So today, start with questions from the homework. Does anybody have anything they want to talk about from the homework?
Oh, yes. I believe it's 13 and 14 where you start off with the zeros and you have to take it back to the cubic function.
Oh, we shouldn't have assigned those.
Yeah. Well, like 15 we could do because it's
Yeah, 15
13
we.
and 14.
Yeah, I don't know why those got mixed in there, huh? We can talk about how to do this though. All right. So let's run through how to do this. All right. So we're told that 5, 8, and -1/2 are all zeros, correct? So that means that like x equals 5, x equals 8, and x equals -1/2 are all solutions. So if I like subtract 5 from both sides, yeah.
That's as far as I got. Well, I asked him the question, so I'm letting you know how far I got.
Yeah, that's okay. With the x plus 1/2, I'm going to multiply both sides by 2 also. It'll just make life a little bit more convenient later on. So each one of these three equations has to be a factor for my polynomial, right? If those are going to be solutions. So I'm going to multiply the left-hand sides of each of those equations together. And I'll multiply the right-hand sides together. So what I have now is the factored form for a polynomial that has those three solutions to it. Now I'm just going to FOIL this out. Yep. So x squared minus 13x plus 40. Yeah, you just need it to equal 0 for the next step that I did here. So I did that, FOILed the first two out together. Now I'll FOIL the next one. So I have 2x cubed plus x squared minus 26x squared minus 13x plus 80x minus 40. And then combine my like terms.
I get like everything underneath the like beginning of like the x minus 5 times the x minus 8 to x minus 1. I get everything under that, but
Okay.
why is cube the x minus 5 times x minus 8 times the x plus 1? Why did those look?
Because what I did is I took each one of these three equations and multiplied them together. So when I multiplied the left-hand sides together, I get this. When I multiply the right-hand sides together, I get 0 times 0 times 0. And what that ensures then is that I have a polynomial with the solutions of 5, 8, and -1/2.
Then with the square root of 5 on the next one, is that
Yep.
just like you do the same thing, but then eventually the square root goes away?
I would square both sides
Square them and then get rid of
to
it.
get rid of it.
Alright.
Yep.
You just have to FOIL it all. So you FOIL x, FOIL x squared,
Could you do 14 as well?
Yeah. Oh, it has Yes, of course. Okay. Boyd?
Can you please explain how to do number 9?
Yeah, we're going to finish 14 first, and we'll circle back and do 9. Absolutely. So we have this, right?
Yeah.
So do the same thing. Get them all to equal 0 now. So far, so good. Okay. Now I'm going to multiply each of these 3 equations together. I lied about squaring both sides. I'm not going to do that because I have both the plus and minus of the same square root. The trick is that I'm going to FOIL those 2 together first, and that's going to make life super easy because that's a difference of 2 squares. Because I have like a minus b times a plus b. So I'm just going to get like a squared times b squared. So I'm going to have x cubed, when I FOIL this out, minus x squared minus 5x plus 5 equals 0. What's up, Olivia? Or Sophia? You guys are mumbling to each other and look upset.
We're just bad at factoring.
You mean foiling?
Well, there you go. There's your answer.
Foiling is when you're multiplying it out.
Like even in the other one, I know like -5 plus -8 is 13. But like what? But 8 times 5 is 40. So how do you get 13?
I just skipped a step. Right? Like I got -5x and then -8x and I added them together. Like I just skipped some steps.
I see. Okay.
Is that okay?
Yeah.
So-
Radicals.
Well, that's a difference of 2 squares, right? This is like a minus b times a plus b. So that's going to just be a squared minus b squared. So I didn't even really FOIL it there. I just used that shortcut. And what's square root of 5 squared? Just 5, right? Because they cancel each other out. Exactly right, yeah. So I really had x squared minus 5 times x minus 1. And that's what I FOILed out below. Does that feel okay?
Yeah.
I'm aiming for more sense. Right? Not all the dollars, but give me the sense.
Yep.
All right. And Boyd, you wanted to look at number 9, is that right?
Change that to number 10.
Yo, who got Mr. Coolidge's calculator?
Yeah, who does got my calculator cover?
Probably.
Oh my goodness.
Yeah, we're there. She saw who?
Okay. So if we're looking for zeros, what do we do first?
Find what multiplies the multiple.
G of x has to be 0, right? Not quite. This problem's a little different than the previous ones I've seen. What's different about this one than the previous problems we've looked at?
Well, we need 2x.
Yeah, we had leading coefficient is not 1. You'd be advised to pay attention to this because we didn't do this type of factoring last time. No, because there's not a greatest common factor of 2 amongst the whole thing, right? So normally we just look for the 2 things that multiply to give us the constant term and add to give us the linear term, right?
Yeah.
Here, we need the 2 things that multiply to give us the leading coefficient times the constant term and add to give us the linear.
The linear coefficient is because the x is just a single x, right?
Here, let's do some color coding.
I get it, I think, maybe. No,
The one.
400 levels.
Alright.
Well, it's pretty much whatever multiplies to negative 6 is what you say.
Right. So we need two things that multiply to give us negative 6, but add to give us positive 1.
So,
3 and
this
negative.
might be a question of why.
Wh-
Wait, never mind, we did this last year, I remember.
Right, and it's always this way, but when the leading coefficient is 1, it just turns into multiplies to give you the last term. Right?
Yeah.
So the common sequencing for this, I think, is what causes this misconception. If I had my say, when I taught like the regular Algebra 2 class, we start with this problem, and then we go to the shortcut method when the leading coefficient is 1. So you learn the one that works every single time, and then get introduced to the shortcut that works in special situations rather than starting with the special shortcut and then learning the generalization. Like, I think the sequencing is just backwards on that. But that's what's going on. Is that okay? Okay. Here's the problem, though. That doesn't give me the factors. What that does is it tells me how to break up that x term. So I need to break that x term up into like negative 2x plus 3x so these two numbers here tell us how to break up that linear term. Because what is negative 2x plus 3x equal? X. Right? It just tells us how to break this thing apart. Once we've broken this thing apart, we make two groups. When we're making these two groups, what do you have to be especially careful about? Has to be a plus sign in between the two groups. What if there's a subtraction symbol there? What should I do? I just write it, instead of subtraction, I write it as plus a negative. And the negative just gets attached to the first term and everything is fine. Everybody's good? So if I look at that first group, I'm going to look for a greatest common factor between 2x squared and 2x. 2x. So if I factor that out, what's left? X minus 1. And then I'll do the same thing for the second group. 3x minus 3. 3. What's left?
And don't they have to be the same on the inside? And then it's like 2x.
If they are not the same on the inside, it means that you've made a mistake somewhere along the way. If this is factorable, this has to work. Okay?
And then
So-
the other, like,
So what I do now is I treat each of those x minus 1s as a greatest common factor for this whole thing. So when I factor the x minus 1, what's left? 2x plus 3. Boyd, is this feeling okay? And then if I set each of these two things equal to 0, I can solve. Negative 3/2, because you subtract the 3 and then divide. That's okay. It happens. Everybody makes mistakes. Just as an aside, this process right here is called factor by grouping. And it's particularly effective when you have an even number of terms in your polynomial. So the key here was rewriting it so that I had 4 terms so I could do the grouping. That's usually the trick. Does everybody feel okay? Okay. The homework quiz scheduled for Friday would be covering like up through 6-2. So just the stuff that we had talked about yesterday. Well, this is homework from yesterday. But I would think I would focus more on like the vocab side.
Do we have a homework?
That's what's on the calendar. It has a question mark next to it. But like,
It's the next day.
oh, okay. Yeah. It's because we're all mutants. That's a comic book joke. It's a bunch of parts because it's just like kind of vocab-y. Yeah. Like if you go back and you look at like
Oh, like your own.
the notes from this day, we spent a lot of time talking about like zeros and maxes and mins and like extrema and like how to write the like it's very like just kind of terminology. Look at the graph and write down what this thing is.
Right.
Like it's not super duper complicated, but if you don't remember the names for stuff, it's going to be rough. You know what I mean? All right. Let's talk about 13.3. I think that's probably all we're going to do today. This is a pretty big, chunky section. So even if we finish more than this and have some time left, I don't really feel like it's worth going any further.
Wasn't it 12.3 the last chapter?
No, I think there's another one after that. It's 13 also. All right. So I need you guys to put on your time machine hats. I need you to go back to like elementary school. Because we need to review how to do long division.
Well, I remember that.
I messed with one.
So somebody give me like a 4-digit number.
4,003.
So actually,
And then a 2-digit number.
1,8.
69. I should have known better. Okay. All right. So let's say we want to do this division problem. How do we start?
You got to put the 4203 within the box. Yep. And the 18 outside of it.
this is actually this one's
Yep.
You guys remember so far?
Then you go 18 goes into 4. No, you put a 0 above it. 18 goes into 42 however many times.
Twice.
2, and then you subtract 36. They're left over. Bring the 0 down. But don't you bring
Only the zero number.
It doesn't matter.
Oh,
I just keep bringing stuff down along the way. It doesn't really matter.
really?
18 goes into, okay, sure. 18 goes into 60. Whatever you guys want.
1836. I'm saving 3 times.
Yep.
I don't know what that is.
6.
6.
Goes in 3 times.
And you get your next
Remainder of 9.
boom.
So how would we write this then? How would we write our answer?
233, then 9 over 8.
Oh.
Great.
The O.
So let's just include a little bit of vocab here.
But couldn't you write that as plus 1?
Yeah. But we're not going to worry about that piece right now. So what is the number 4,203 called?
Oh.
That's the dividend. What's the 18 called?
The divisor.
That's the divisor. The 233 is called
Product. No, quotient.
quotient.
Product.
The 9 is the,
Remainder.
and then 18 is the divisor once
I
again.
should write this down for myself. This is gonna be rough.
Okay? So we can do this for any two integers, right? We can rewrite any integer divided by something as a quotient plus remainder over divisor. Okay? Okay. Let's do this then for a polynomial. Oh boy, that's real small.
One more, man, then we have wrapped it.
I don't know how to do that. Oh, yeah, I do. Just ring that bell. So,
I want that for you.
Okay. So we're going to get to that also.
that's good.
So well, how do I start my setup here?
It's not that bad. You just have to wait until you get to the second.
Okay.
Minus 3
Divided by our
that big
top.
number of times.
The big girl up
Big
top.
dog.
The
Okay.
big dog on top.
Big dog.
Now, this is fine. I would not write it this way.
Got it.
I would, do you notice something odd about x squared minus 3?
Alright.
It's not fun.
Well, we could just write it as x minus 3
Negative
parentheses,
x.
right? No.
I wouldn't do that.
Can we simplify?
Is it missing something?
Oh, it's missing our other
It's
x.
missing an x.
It's
Missing an x term, right?
plus 0 x.
So I would include a 0x term there.
Alright.
Now, is it critical that I do that? No,
But it helps.
but it's going to help keep everything lined up so I don't have to think about it later on. So I'm going to include it because it's going to help. All right. So now I'm going to ask myself, what, actually, I'm going to write here, what times 2x cubed, or times, sorry, what times x squared gives me 2x cubed? 2x. Oh boy, what just happened? So 2x goes here. I'm now going to multiply that to the entire divisor, and I'm going to write it below. And we're going to subtract down. The most common mistake students are going to make is subtracting wrong. My suggestion to you is once you've written it this way, to immediately distribute the negative.
You're trying to get rid of the 2x. I'll explain it.
Okay, if we then add down 2x cubed plus a negative 2x cubed is 0. Negative 4x squared plus 4x squared, or 0x squared is negative 4x squared. 5x plus 6x is 11x. And then I'll bring down the plus 1. And now I'm going to repeat the process. I'm going to ask what times x squared gives me negative 4x squared. Negative 4. I'm then going to multiply that to all the parts of my divisor. And at this point, you should be seeing why I included the 0 in there, right? We'll subtract down. Oops, that's plus 12. Now, what am I going to do next? Distribute the negative through. So that becomes plus, plus, and then this one becomes minus. Everybody's okay? Negative 4x squared plus negative 4x, or I'm sorry, plus 4x squared is just 0. 11x plus 0 is 11x. 1 plus negative 12 is negative 11.
Because you have to change the negative. Or why did we add? And then we wanted the negative.
Sophia, instead of subtracting the entire polynomial, I distributed the negative sign through and turned it into an addition problem. Because the most common mistake students make is they put the negative sign on the first term and then they forget about it for everything else. I'm saying distribute the negative through to start so that you can't forget it and then just add down. Right? Instead of thinking about it as a subtraction problem, I'm going to think about it as plus a negative.
Plus right there though.
I've used
In the
it.
beginning.
I did.
Like plus.
It's the same as this plus. Right? I'm just indicating that I'm adding the negative down.
Alright.
Because originally I started with like, it was negative. It was originally written like
See
this,
what you did.
and then I went through and turned it into plus the negative. Is that
Yeah, no, now I get it.
okay? Okay. So how am I going to rewrite this as my final answer then? Because it wants it in quotient plus remainder over divisor.
X minus 4.
Hmm.
Plus
Parentheses.
11x
X squared minus. Not.
You don't need a parenthesis anywhere. You could put one. I mean, if you want to do this, you can. It's not wrong. It's not necessary either. Are we okay with how I've written this? Okay.
Oh, yeah.
So the remainder theorem says that if you have f of x, where f of x is a polynomial, and I divide it by some x minus k, some other linear binomial whose leading coefficient is 1, that kind of polynomial is called a monic polynomial, where the degree is 1 and the leading coefficient is 1. Then the remainder of f of x divided by x minus k is going to be the same thing as f of k. So I can plug in the value for k and just evaluate the function, and whatever that number is will be the same as my remainder. Monic, yes. That's just a vocab word for that kind of polynomial.
I know.
All right. So here it says find f of 2 using the remainder theorem. So that would tell me that k is 2. So I'm going to do f of x divided by x minus k. Or really just divide by x minus 2. So there's my start. Multiplies to x and gives me 2x squared is 2x. I subtract down. What should I do first? Sophia? Distribute the negative. So that's going to be plus a negative then, and that'll become just positive. We add down, we get 0 minus x plus 4. So then I'm going to ask myself, what times x gives me negative x? Negative 1. Distribute that across. Subtract down. But what should I do first? Distribute the negative. So that's really going to become plus and then minus. So I get remainder 2. So this tells me then that f of 2 is equal to 2.
That's it.
That's it. Contrary, what if we wanted to go the reverse way? This is the more useful. What if we ask instead the remainder for f of x squared minus 5x plus 4 divided by x minus 2? Is I don't have to do any polynomial division with the remainder theorem. All I have to do is plug 2 in for f of x. Boy, that was a heck of a lot easier than doing the long division, wasn't it?
So that was like the same thing, just a shortcut?
It's the reverse idea.
Oh.
It's the reverse idea. All right. So we've seen this remainder theorem go back and forth, right? Where we can use like substitution to find a remainder, or we can use a remainder to get a substitution value. What remainder, if we think about this in terms of factoring, is going to be the most important remainder? The one that would be most interested if the end goal is to be able to factor things? What remainder, if we're looking to be able to factor things, what remainder would indicate that something is factorable? 0, right? If I get a remainder 0, that meant that whatever the divisor was is a factor, right? So that's what we're going to call the factor theorem. We say that f of x has the factor x minus k if and only if f of k is equal to 0.
always just do long division? It's your answer.
Well, so here's what we can say is that what's the k in this case? What?
Would it be 3?
It's -3,
Oh.
right? Because it's x minus k. Basically, you're setting that divisor equal to 0 and solving. So if I do f of -3, what do we get? 6 times 27 is 162. 9 times 25 is 175. Oops, that's -162 though. -3 times 16 is 32. -48. And then minus 15. Oh, 25 times 9. That's 225, excuse me. So what I get there is 0. Right? So what I know then is 625, or 6x cubed plus 25x squared plus 16x minus 15 is going to equal x plus 3 times something, right? Here's the problem with what we just did. Does what we just did give me what that something is? No. How am I going to have to, what am I going to have to use to get that something? I have to do the division, yeah. So although that factor theorem and the remainder theorem I can kind of pair together to check really quick if it's factor, like if that thing is a factor, it doesn't really tell me anything about how to do the factoring. That's going to change here in a minute. But for right now, we're stuck with it the way it is. So let's see, 6x squared. I'm just going to kind of burn through this real quick to show you the result. Is that okay with you guys? Okay, we've done a couple of examples of this now, so it shouldn't be too bad. So what do you get? 7x squared plus 21x. So what is my question mark then? The quotient. Now, this process of doing the long division to find these factors kind of el stinkos, right? This takes up a lot of space. It's relatively time consuming. What we'd like to do is find a way to where I can basically just do this and somehow also get this to come out also. The way we do that is called synthetic division. Now there's a couple of catches for synthetic division. This is a special case for the long division. Long division will always work. You can always do long division. You cannot always do synthetic division. We can only do synthetic division when the divisor is monic. Something like x minus k. right. And you guys kind of remember doing synthetic division last year? Remember the name, maybe once you see the process, it might ring a bell. You also called it synthetic substitution possibly last year. Because that's, again, what this really is a substitution that you're doing. It's also just getting you the long division part to it. So I start by kind of drawing my synthetic division bar. And the coefficients for my dividend are going to go up here. Now, what is the thing I have to be real careful about with those coefficients? Even more than positive and negatives, if I skip a term in my polynomial, I have to include a 0. In the long division, if you're paying attention and you make sure everything is lining up, it doesn't matter if you forget to put the 0 in or not. I think it really helps to make sure everything feel like it makes more sense and it lines up, so like terms line up with like terms. But if you're paying attention, it's not a big deal. Here, if you forget the 0, you cannot recover, you cannot get to the correct answer without it. Gotta have it. Now, what number is going to go on the outside here? You just take the divisor, set it equal to 0, and that's the number that goes on the outside. So that's the setup for synthetic division. Does anybody remember the first step?
Yeah, that's what I meant, yeah. Like just 6,
Mhm.
and you do 6 times.
Right, then we do -3 times 6. We write our answer in the next spot, and then what do? Add down. And then we just keep repeating that same process. You guys remember doing that process? So here's the key. Now, somehow these numbers at the bottom tell me everything that I need. The way you read these numbers is from right to left. That's contrary to all other reading that we do. So the number on the far right is the remainder. The next is our constant term. The next is our x coefficient and our x squared coefficient. So what we can say here is this polynomial divided by x plus 3 is equal to the quotient 6x squared plus 7x minus 5 plus my remainder over divisor. What is this? That's just 0, right? If I have a fraction whose numerator is 0 and the denominator is non-zero, it's just 0. So that's just gone. And if I multiply both sides then by x plus 3, what I have is my factored form. So just to reiterate, this synthetic division gives me, as the power of just doing the substitution, right? There's the 0 that's the output for the remainder, but the process along the way gives me the other part of my factor. This is our kind of our gold standard. We'll use this much more often than we would long division. In fact, whenever it's possible to use this, this would be the preference. It is much faster, much less space, gets you the same information. Way easier to not make a mistake doing this than the other one, I think, because there's less just like negative signs rattling around and less arithmetic that's happening. This is just numbers. There's no variables going on. I think it's a much easier process. Yes. So if the divisor is not monic, so it has to look like x minus k or something, where the leading coefficient is 1 and the degree is 1. If it doesn't have that, don't use synthetic division on it. You can make it work if the leading coefficient is 1, but you got to be kind of sneaky about it. But you can't even get it to work if the leading or if the degree isn't 1. You're welcome. So again, we want to be quite careful. So notice here, when we did this synthetic division, this could be thought as the process of 6x cubed plus 25x squared plus 16x minus 15. Or you could think about this as just like f of negative 3 right? That last output is the same thing as the value when we make our substitution, right? So you can use this in the same way, use the same process to do something like the following. So if I were to do this the long way, I would do this, right? Everybody's cool with that? Or I can use what I've just learned and do this kind of using the synthetic division. Why did I write that 0 there? Yeah, very good. There's no x cubes, so I need to make sure I put a 0 there. And now this will run just like the other. Oh, shoot. That's 4. I'm sorry. That's 475, not 95, dum-dum. So that's 468. There we go. Okay. So again, whether we're doing substitution or checking for divisibility or trying to use this as a factoring, the process is the same. It's really flexible in that way, and that's really nice that it can, the same process like accomplishes multiple different tasks, right? Yes. I like having like one tool that just kind of does everything, right? That's nice. All right. Next piece is called the rational roots theorem. And this says that we should say the only possible rational zeros for a polynomial are of the form p divided by q, where p is a factor of the constant term, and q is a factor of the leading coefficient. So I just abbreviated LC for leading coefficient there. This is going to be a super important theorem. We're going to use this a whole heap. So let's do an example. So what's my constant term for this polynomial here that I've written? Yeah. So what are my factors of 4? Well, and -1, and -2, and 4. Everybody agree? What's my leading coefficient? 3. What are my factors of 3? Okay. So my possible rational zeros are going to be any factors of 1, or the factor of 1 divided by the factor, plus or minus 1 divided by plus or minus 1, plus or minus 2 divided by plus or minus 1, plus or minus 4 divided by plus or minus 1. When I divide anything by 1, what do I get? Yep. And then I'd have plus or minus 1 divided by 3, plus or minus 2 divided by 3, and then plus or minus 4 divided by 3. So that's the total list of possible rational zeros. Everybody okay there? You remember doing this last year maybe? You do this a lot. So this is one that you should remember. Okay. So the next thing we're going to want to talk about is showing if a zero is a upper bound or lower bound for the set of zeros. So I'm going to just screen grab this and drop it in because it's kind of a lot to write. So if f of x is a polynomial with a positive leading coefficient, and we divide by k using synthetic division, if k is a non-negative, and then every number on that bottom line of our synthetic division is a non-negative, then k is an upper bound for all the zeros of f. If k is non-positive, and every number on that bottom line is alternating from non-negative to non-positive. So again, that's greater than or equal to 0, or less than or equal to 0, then k is a lower bound for all of the zeros of f. What does upper bound and lower bound mean? It would mean it's bigger than all the possible zeros, and lower bound would mean it's smaller than all the possible zeros. So let's just do an example. Yes. Yes, of course. He's had a hard day of killing knights and stuff. It's exhausting. Those magic archers and things.
Archers and wizards and stuff.
Yeah.
The Mega Knight gets thrown down, you never know.
All right. Let's try to refocus here, folks. I know there's a lot of stuff going on. All right. This example says, show that every real zero of the polynomial f of x equals yada, 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 lies on the interval -5 to 4. So the -5 is in theory a lower bound, and the 4 is an upper bound. That's what we need to show. Okay. Now, this appears to sound like a lot, but it's not. All it is 2 synthetic divisions. So I'm going to do a synthetic division with -5, the lower bound. And what are we looking for here? I'm sorry. Alternating from non-negative to non-positive. So far, so good. Everybody cool with what we got? Yeah, we alternated from non-negative to non-positive. So that tells us that -5 is a lower bound. So all of my zeros have to be bigger than that.
So they have to alternate.
Mm-hmm.
If they don't,
Then it's not a lower bound. So to show something as an upper bound,
So is the first one in the interval lower bound? Or is
well, that would have to be, I mean, the bigger number couldn't be the lower bound, right? Like it always has to be that way. So I'm just going to do another synthetic division just with the other end of my interval. And as Nathan has pointed out, the first number in your interval always has to be the lower bound, and the second number in your interval always has to be the upper bound. We just have to show that it works. So what do we see here? All greater than or equal to 0. That's what we need. So 4 is an upper bound. Since that's the case, we know all the zeros of f of x are greater than or equal to -5 and less than or equal to 4. So they're on the interval from -5 to 4. All right. Let's put some of these ideas together, because in the end of the day, what are we really most interested in? What did we start with in this chapter looking for? The zeros, right? Let's take something that we can't solve by factoring and show us how we can use all of these ideas that we've established so far to find the zeros for a polynomial. So what's the first thing I need to do if I'm looking for the zeros for a polynomial? Yep, we set it equal to 0. Sure. How many possible zeros would we be looking for?
3 at most.
Great. Since the degree is 3, we know there's at most 3 zeros. And of those 3 zeros, we want to figure out the ones that are possibly rational. How do we do that? The constant term. What are the factors of negative 30? 1, 2, 3, 5, 6, 10, 15, and 30. And the leading coefficient is 6. No, you could use your calculator if you wanted to.
I don't know how to use my calculator for this. Someone's gonna show me.
I mean, all you do is you go, does 30 divide by 1 give me a whole number? Yes, okay, then 1 is on the list. 30 divided by 2, is that a whole number? And in fact,
like I could plug it in and be like 1, 2, 3, 5, 6.
no, it won't do that.
I
I mean, you could write a code to have it do that, but it wouldn't be too hard to do. It'd be potentially time consuming. Yeah.
You can put like games in it or something.
Yep.
Oh yeah, I had Blackbird on my.
So this is going to be a long stinking list, right?
Yeah.
So I'm just going to, well, we'll start, but I'm going to just do, well, let's write the whole second set, because there's some simplifying we can do. Shh.
Do you have to put 2 over 2?
Well, we're going to get there in just a second. Yes, you do not. But I figure we should do it naively here at first. So on this list, Nathan's pointed out 2 over 2, that's 1, and we already wrote 1 here. Do I need to include that then? What other, yes, go ahead. What others don't I need to include?
600.
And then we can just kind of keep going, right? Now there's, what is there? There's like, I don't know, 30 things on my list or some stinking number. It's like too many to check. Is there a way for me to narrow this list down to give myself a better idea of what I should try to start my synthetic division with? Yeah. What are the zeros the same as graphically? They're x-intercepts. So what I'm going to do to start then is I'm just going to go and graph this function on my calculator. I'm going to look for any x or any x-intercept that I can identify. I don't really care what it is, just something that I can tell obviously. And that's what I'm going to choose to use to start my synthetic division. So I'm just going to do a zoom standard on this and put on a normal window. So I see 3 places where my graph is crossing the x-axis, right? So I have this one that's somewhere between 2 and 3, this spot somewhere between 0 and 1, -1 and 0, and this one that looks like -6. I think it's exactly -6. Which one of those do you think is going to be the easiest one to do the synthetic division with? The whole number. Let's use -6. Okay? Now, the natural question is, why don't I just start with, why don't I just use the graph to get the answers here? My question should be, why did I bother doing this stuff and not just go straight to the graph? I need to check to make sure that these things, before I use them, are on my list somewhere. Right? Because if they're not on that list anywhere, what does that tell you about that possible number? It could be in a 0. It would mean that it's irrational. It means that it would have to come as the result of like a quadratic equation or a quadratic formula to solve. It'd have like a square root in it or something.
So you don't want that?
You do not want to use those. That's going to be a nightmare. Because unless you can tell what the square root is, you can't use the synthetic division on it. Please stop talking. So I'll go ahead and I'll do my synthetic division now. 6 times 13 is 78. So that's done. I'm super excited because I got 0 for my remainder. So what that tells me then is 6x cubed plus 23x squared minus 83x minus 30, the original problem, is equal to x plus 6. Where is that coming from?
That's coming from this.
That's from the divisor, right? Times 6x squared minus 13x minus 5. Where is that coming from? That's the quotient, yeah. Everybody okay there?
Yeah.
So if I want to solve this now, remember this is equal to 0. So I can say x plus 6 has to equal 0, and 6x squared minus 13x minus 5 has to equal 0. Well, easy enough to solve x plus 6 equals 0. How do I solve 6x squared minus 13x minus 5 is equal to 0? You could try to factor that. Or what I would prefer to use in this case, since the leading coefficient isn't 1, I would use the quadratic formula. Very good. You may. You're welcome. So when I do that, I get 13 plus or minus 169 minus 120. 169 minus 120 is 49. The square root of 49 is 7. So 13 plus 7 is 20 over 12, which reduces down to 5/3. And 13 minus 7 is 6/12, which reduces down to 1/2. So those are my other two solutions.
So those are our solutions.
Yep. Yeah, whatever. What do you guys think here? We'll talk about what's due on Sunday in just a second. So you guys should be able to do up to 43 now. So that would be 16 to 43. But we don't need to put this in this Sunday's problem set,
Shoot it to,
right? That's fine. We can do it in the next one. And in
that.
yeah. So
Well, I just did it based off of what we did yesterday.
So, Mr. Coolidge, all that's due this Sunday is 1 through
I pretty much just went through the steps that he went through.
so 219 is just gonna be 1 through 15. And then the following Sunday, well, that's still break, right?
Yeah.
So let's say 3-5 then.
It's just one through.
That'll go into the next 3-5 homework. Okay. Next class, again, what are we doing on Friday on the X day? Homework quiz. Guess what you're going to have after the homework quiz to work on? Some Delta Maths, yeah. Really just 6-1 and 6-2 is the homework quiz, Sophia. And I think you guys are